Hi, and welcome to another lecture in fluid mechanics. Over the past few lectures, we've learned to solve for velocity fields for channel flow and pipe flow, a special set of solvable enclosed flows. We solved for the velocity field, u, v, and w, and the pressure field, p, in both Cartesian coordinates and cylindrical coordinates. Today we're going to explore what to do with these fields. Sure, it's nice to plot the velocity, but in practice we want to be able to get meaningful quantities from the velocity field. The quantities we will cover today are the average velocity, max velocity, volumetric flow rate, shear stress, and wall force. All these can be calculated directly from the velocity field. We will also go through some practical examples so that you can see how professionals might utilize these equations in a work scenario. Let's jump right in. Recall the different types of enclosed flows we've encountered. We've seen pressure-driven channel flow, which is flow between two flat plates driven by a pressure gradient, with the following velocity fields solved for. Gravity-driven channel flow is angled and driven by gravitational body forces, which has the following velocity fields. And viscosity-driven channel flow, called co-wet flow, where a moving wall pulls the fluid via viscous forcing, results in the following velocity field. We've also tried pressure-driven pipe flow, where flow is pushed via pressure forces through a level pipe and the velocity field is in cylindrical coordinates. For each case, we found that v and w were 0, but they did have unique streamwise velocity functions. You may be asking yourself, okay, what do we do with these equations? How do we make practical use of them? Well, from the velocity and pressure field, we can calculate some pretty useful quantities. First, we'll consider maximum velocity, Umax. Knowing this would help you select sensors, determine where to put your sensors, and know about the average particle transport in your flow. Second, we can calculate the average velocity, which can tell you things about the average amount of time it takes the fluid to transport something from one place to the other. Third, we can calculate the volumetric flow rate, Q. This tells us how long it will take to empty a reservoir, how much fluid you might need, or pump selection. And last, we calculate the wall shear and drag force, tau and d. This tells us how much force the fluid exerts on boundaries, which is critical in areas like aerodynamics and hydrodynamics, where the focus is on vehicles moving through fluids. These are all quantities we should be comfortable knowing how to calculate if we want to make use of the fluid mechanics in the real world. Today, we're going to learn by doing. A few examples will show us how to calculate these quantities for some different situations. Consider pressure-driven channel flow. We have flow driven by pressure difference between two flat plates. The flow has a parabolic velocity field where v and w are 0, and u is some function of the pressure gradient and viscosity. Let's say we're simply interested in the maximum velocity in the pipe. Maybe we're measuring the velocity in the pipe center, and we want to know what sensor to choose. From the pressure gradient, which is easy to estimate or measure in application, we can get this max velocity assuming the flow is laminar. The maximum velocity happens by calculus definition, where the slope of the velocity profile equals 0. For a parabola, this is right in the middle, but let's officially calculate it. First, solve for the y location where du dy is 0. Since we know the first group of terms is non-zero, we can assume that what's in the parentheses has to be 0. This gives us that 2y minus a equals 0, which means that y equals a over 2 when the velocity is max. This is the middle of the channel. Plug this y into the original velocity function, and this gives us the velocity at the location of the max velocity. Thus, we have the max velocity directly calculated. Please note that some of the equations in this lecture are general, and some apply to the flow we're using at that time. For example, This Umax equation changes depending on what flow you're considering, so it's important to keep your flow field in mind when using these equations. Here, if we know the pressure gradient, we know the maximum velocity that occurs in our channel. Let's move on to another example that's a bit more practical and shows off how we can utilize fluid mechanics in the real world. Let's say you're a new engineer and you're tasked with finding the volume of a water reservoir. Here we have a triangular reservoir that, near the bottom, opens into a parallel plate flat flow. The reservoir has width W, angle gamma, and height h. Unfortunately, we don't know h because we cannot see or measure the water level. We can assume that the flow between the parallel plates A to B is gravity-driven channel flow. The reservoir is long enough into and out of the page that end effects are negligible and things are relatively two-dimensional. Let's set up a small diagram with your channel flow parameters. Our goal here is to solve for how much water we have. Maybe you're using this to supply a village and you want to know how long you have until water runs out. Unfortunately, we don't know h, so we can't calculate the volume directly. Let's use fluid mechanics to help us. The tools we are given are a bucket of known volume to catch the water and a stopwatch to measure the time. That's it. We're going to use our knowledge about gravity-driven channel flow to estimate the reservoir volume. Our strategy will be to use the stopwatch in the bucket to measure the volumetric flow rate, then from there we can get the pressure gradient. The pressure gradient gives us the pressure at the bottom of the reservoir, and from that we can use hydrostatics to get the height h and eventually the reservoir volume. Let's do it in steps 1 through 4. The first thing we need to do is take a measurement. Use your bucket of known volume and time how long it takes to fill it up. This volume per time is the volumetric flow rate. Volumetric flow rate also has a formal definition that can be calculated from a velocity field. It is the integral of the velocity across an area. You can use this relationship for any type of flow where you know u. We know the velocity field for gravity-driven channel flow because we solved for it a few videos ago. Here, u is a function of viscosity, the pressure gradient, and the body force of gravity. This is a special case because the channel is vertical, so dh dx is -1. U reduces to the following function. The volumetric flow rate is the integral of the velocity profile over the cross-sectional area. Our channel is essentially a big rectangle, and the flow profile is constant across the width because we've assumed things don't change in the z direction. That means we can just integrate the velocity profile across the channel height and multiply by the width. Do out this integral and we get an expression for the volumetric flow rate as a function of the pressure gradient and a bunch of known quantities. Note that if we were interested in the average velocity, we get it from the flow rate. You just divide the volumetric flow rate by the area. This is a general flow property and can be used for any flow type. With our new volumetric flow rate, we can solve for the pressure gradient dP dx. Here, Q is known from our bucket measurement in step 1, where we measured how long it would take to fill a given volume. Now we need to take our known pressure gradient and calculate the pressure that's at the bottom of the reservoir, which is the top of our channel. Let's take the pressure gradient in differential form and estimate the average pressure gradient as the difference between the pressure at the entrance and exit of the channel divided by the channel length. Plugging in our equation for dP dx above, we can now solve for the pressure at point A. The exit of the channel is ambient pressure, which is known, so we can use that for PB. This gets us an expression for the reservoir pressure where all the variables in the equation are known. In the last step, we use our knowledge of hydrostatics because we assume there is no flow in the large reservoir. Calculate H by knowing that the pressure at the bottom of the reservoir is the product of the gravity, density, and water surface height. Plug in our expression for PA and solve for H, which is another relatively complicated function with all known variables. Once we know the water height, it's just a matter of geometry. We can use the geometry of a triangular column to calculate the reservoir volume. For this geometry, the area is h squared times tan of gamma over 2. This, multiplied by the width, is the volume of water in the reservoir. And there you go. Through a series of basic fluid mechanics relations, we were able to estimate the volume of a large, oddly shaped reservoir with only a bucket and a stopwatch. With this example, we learned that practical things can be achieved with textbook fluid mechanics relationships and that there are practical applications to using the velocity field. Also, we inadvertently learned how to solve for the maximum velocity, the average velocity, and the volumetric flow rate for general flow situations. Lastly, let's consider the shear stress and drag imparted by the fluid on the wall for a different flow problem. We haven't considered pipe flow yet, so let's do it for pressure-driven pipe flow. Let's briefly set up our flow and label everything important. In the last video, we learned how to solve for the velocity field of this flow, which gave us the following velocity relationships. Keep in mind that we've swapped to cylindrical coordinates here. Let's estimate the force that the pipe feels due to the flow in the pipe, which is primarily due to viscosity. Newton's law of viscosity states that the shear stress, tau, is the viscosity times the velocity gradient. Let's plug in our expression for ux into this equation to find tau. We get a fairly simple equation for tau as a function of the pressure gradient and radial location. This wall shear stress changes depending on where you are in the pipe. Let's plot the shear stress profile across the r coordinate. At r equals 0, the pipe center, the shear stress is 0 because the slope of the velocity is 0. And at the wall it's the maximum. All of the force the fluid imparts on the pipe is done at the wall. It's where they meet. So the drag force felt by the fluid is a function of the shear stress at the wall, where little r equals big R. If we plug big R in for little r into our tau equation, we get the shear stress at the wall, tau sub w. We could calculate the force applied by the fluid on the wall by multiplying this wall shear stress by the area that it acts upon, because force is the stress times an area. In this case, the area would be the inner area of the pipe over a certain length. Please keep in mind that this again is a problem-dependent equation. Tau wall depends on the flow type and so does the area calculation. To summarize, after these 3 practical working examples, we have learned how to calculate the following for flow fields. The average velocity is the volumetric flow rate divided by the area the flow passes through. The max velocity is the velocity field evaluated at the y location where u is max, which is when the slope of u is 0. The volume flow rate is the area integral of the velocity, which has separate forms for channels and pipes. The shear stress profile is the viscosity times the velocity gradient, which is Newton's law of viscosity and is different for pipes and channels. And lastly, you use the shear stress at the wall times the wall area being acted upon to calculate the viscous drag force. And that's it. We will need these quantities moving forward to further analyze flows practically and make good use of them. Let's review. We started by reviewing the enclosed flows we've learned to solve completely for the velocity field. Our goal was to find useful practical quantities from these velocities. The channel flow example taught us how to find the maximum velocity. Using a series of basic relationships, we were able to solve for the volume of a reservoir with only a bucket and a stopwatch. Along the way, we learned to calculate the volumetric flow rate and average velocity. And last, we used a pipe example to consider the wall shear stress and the force the pipe feels because of the fluid moving through it. These relationships are commonly used in practice, and you'll make use of them in your fluids careers. I hope you liked the video, and thanks for watching.